The universe holds 26 secrets in the very fabric of reality. Spacetime itself is not an empty stage, but a dynamic, living tapestry woven from gravity, light, and time. Each thread contains a clue, a piece of a cosmic puzzle that could completely reshape our understanding of existence. From the silent echoes of colliding black holes to the ghostly pull of invisible matter, these are not just abstract ideas. They are real phenomena that challenge everything we think we know. By the end of this journey, you will see the cosmos in a completely new light. What happens to matter that falls into a black hole? How can empty space have energy and structure? We are about to uncover the answers together. What do you believe is the universe's greatest hidden mystery? Einstein's revolutionary idea was that space and time are not separate, rigid entities. They are fused together into a single, pliable substance, a fabric that reacts to the universe within it. This four-dimensional continuum means that every event, every moment, exists as a unique coordinate woven from both location and time. The presence of matter and energy does not just sit within this fabric, it actively shapes it. A planet or a star creates a depression, much like a bowling ball settling into the center of a stretched trampoline. This curvature is what we experience as gravity. Objects are not pulled by a mysterious force, they simply follow the natural curves and dips in the spacetime around them. This elegant concept explains why an apple falls to the ground and why the Earth orbits the Sun. Both are just traveling along the invisible contours of warped spacetime. Without this foundational understanding, the deeper mysteries of the cosmos would remain locked away. But with it, we are ready to witness the first incredible clue written into this cosmic fabric, a phenomenon that acts as nature's ultimate magnifying glass. Einstein's century-old prediction finally found its proof in a faint, almost imperceptible chirp. In 2015, scientists at the LIGO observatory detected the unmistakable signature of gravitational waves. These were ripples in the fabric of spacetime itself, born from the violent merger of two black holes more than 1 billion light-years away. Think of spacetime as a still pond, and these black holes as two massive stones dropped into its center. The collision sent out ripples that traveled across the cosmos at the speed of light, subtly stretching and compressing everything in their path by a distance tinier than the width of a single proton. By the time these waves reached Earth, they were whispers from an ancient cataclysm. This discovery did not just confirm a brilliant idea, it gave us an entirely new sense with which to explore the universe. We are no longer just stargazers, we are now listeners to the cosmic symphony. Each new detection, each ripple from colliding neutron stars or dancing black holes, adds a new note to this song. These waves carry encoded information about the objects that created them, their masses, their spins, and their terrifying power. They are direct messengers from the most extreme environments, allowing us to hear events we could never hope to see. And as we build more sensitive listeners, we will hear the faint echoes from the very birth of the universe, a time when spacetime itself rang like a bell. This new sense is already revealing the universe's most violent secrets, but to understand them, we must look directly into the abyss, to the places where the fabric of reality is stretched to its absolute limit. This boundary of no return is where spacetime itself is bent into a perfect trap. The event horizon is not a physical surface you could touch. It is a mathematical point of no escape, a one-way door in the cosmos. Once anything, even light, crosses this threshold, it is lost to our universe forever, its information seemingly erased from existence. This creates a profound puzzle for physics, a conflict known as the information paradox. If the laws of quantum mechanics state that information can never be truly destroyed, what happens to all the detailed data about an object that gets sucked into a black hole? Stephen Hawking tackled this by showing that black holes are not entirely black, due to bizarre quantum effects occurring right at the edge of the event horizon. They slowly leak a faint glow of radiation, causing them to evaporate over unimaginable eons. But does that radiation contain the scrambled secrets of everything that fell in? Modern theories now suggest the event horizon might not be the smooth, perfect barrier we once thought. It could be a chaotic, seething region of quantum fuzz, a place where information is not destroyed but is instead encoded onto the surface in incredibly complex ways. This is not just theoretical, we are now photographing these cosmic edges. The Event Horizon Telescope gave us our first stunning image of the shadow of a supermassive black hole, a dark silhouette surrounded by a fiery ring of light, which is the event horizon itself. By studying these boundaries, we are not just looking at darkness, we are probing the absolute limits of gravity, testing if these gates could hide even stranger passageways like wormholes. But to truly grasp the power of a black hole, we must consider its most mind-bending effect, one that warps time itself. Even our most trusted companion, time itself, is not the constant we believe it to be. This is the third profound clue woven into spacetime, a phenomenon called time dilation. Einstein's theory of relativity tells us that time flows at different rates depending on where you are and how fast you are moving. In a stronger gravitational field, like that near a massive planet or a black hole, time actually slows down. This is not a philosophical idea, it is a measurable physical reality. Scientists have proven this by flying incredibly precise atomic clocks on airplanes. When they compared these clocks to identical ones left on the ground, the clocks that had traveled at high speeds were ever so slightly behind. This effect is not just a laboratory curiosity, it is essential for the technology we use every single day. The network of GPS satellites orbiting our planet is constantly moving at high speed and is also farther from Earth's gravitational pull. Because of this, time passes slightly faster for them than it does for us on the surface. If the satellite's internal clocks did not account for this tiny difference, the entire system would become inaccurate in a matter of minutes, and your navigation app would lead you astray by several miles. This reveals a staggering truth: time is not absolute. It is a flexible dimension, deeply interwoven with the fabric of space and gravity. Imagine an astronaut on a daring mission skirting the edge of a black hole. For every hour they experience, decades or even centuries could pass for everyone back on Earth. They would return to a future world that had moved on without them. This is the ultimate consequence of time dilation, a concept that feels like science fiction but is grounded in undeniable physics. It challenges our most basic perception of cause and effect, suggesting that the steady tick of a clock is merely a local perspective, not a universal rule. By studying how gravity and motion sculpt our temporal experience, we gain direct insight into the fundamental symmetries of the cosmos. And if gravity can bend time, what else can it manipulate? It can even twist the path of light itself, creating cosmic illusions that trick our eyes and reveal the hidden mass of the universe. This bending of light is not a flaw in reality but a feature, a powerful tool gifted to us by the warping of spacetime. When a massive object like a galaxy cluster sits between us and an even more distant light source, its immense gravity acts as a colossal lens. It curves the very fabric of spacetime so dramatically that the path of light traveling through it is forced to bend. The light from the background object is distorted, magnified, and often smeared into strange, beautiful arcs or even perfect circles of light known as Einstein rings. These are not physical rings, but cosmic mirages, optical illusions created by the universe itself. The Hubble Space Telescope has provided us with breathtaking portraits of this phenomenon, showing distant galaxies stretched into shimmering halos around closer clusters. But the true power of gravitational lensing goes far beyond creating pretty pictures. The precise amount of bending we observe tells a story about mass, specifically about mass we cannot see. When astronomers measure these distortions, they often find that the visible matter in the foreground galaxy is not nearly enough to account for the intense lensing effect. There must be something else there, a huge amount of invisible mass providing the extra gravity. This is one of the strongest pieces of evidence we have for the existence of dark matter. By mapping how light is bent across the sky, we are essentially drawing a map of where this mysterious substance resides, tracing the hidden skeleton of the cosmos. This natural telescope also allows us to peer further back in time than ever before, magnifying the faint glow of the earliest galaxies that formed after the Big Bang. It is a perfect demonstration of how the curvature of spacetime, once just a theoretical prediction, has become one of our most vital instruments for discovery. It reveals that the universe is filled with far more than meets the eye, and that the greatest source of gravity in the cosmos is not the stars and galaxies we see, but something entirely unknown. This invisible substance provides the very framework for our cosmos. We have never directly seen dark matter, we cannot touch it, and it does not emit or reflect any light. Yet we know it is there because of its unmistakable gravitational footprint on the fabric of spacetime. It reveals itself in the way entire galaxies spin. The stars at the outer edges of a spiral galaxy are moving so fast that the gravity from all the visible matter, all the stars and gas we can see, is not nearly strong enough to hold them in orbit. According to the laws of physics, these galaxies should fly apart, yet they do not. Something unseen, a massive halo of dark matter, must be providing the extra gravitational glue to keep them intact. We see its handiwork in the way giant clusters of galaxies bend the light from more distant objects through gravitational lensing, an effect far too strong to be caused by visible matter alone. From these observations, scientists estimate that dark matter makes up about 27% of the entire universe, far more than all the atoms and stars we see combined. It is the cosmic scaffolding, the hidden skeleton upon which galaxies are built. Without its gravitational influence, the universe would look completely different, and structures like our own Milky Way might never have formed. The leading theory suggests dark matter is made of exotic particles that do not interact with light or ordinary matter except through gravity. They could be passing through you and everything around you right now, completely undetectable by any conventional means. This means the majority of the universe's matter is fundamentally alien to our experience, a ghostly presence woven directly into the space-time we inhabit. Solving this mystery requires us to look beyond known physics, to consider forces and particles we have not yet discovered. But if dark matter is the hidden mass holding the universe together, what is the mysterious force that seems to be tearing it apart? The very fabric of space itself seems to be fighting back against gravity's pull. In the late 1990s, astronomers made a discovery so shocking it earned a Nobel Prize. They were measuring the distances to incredibly far-off supernovae, using them as cosmic mile markers to track the universe's expansion. Everyone expected to find that the expansion was slowing down, gradually decelerating under the collective gravity of all the matter in the cosmos. But the data told a completely different story. The universe was not slowing down at all. it was speeding up. The expansion is accelerating, as if some mysterious, invisible force is giving it a powerful push. This force was named dark energy, and it is the sixth profound clue hidden within spacetime. We now believe this dark energy makes up about 68% of everything in the universe. It is the dominant component of reality, yet we have almost no idea what it is. The leading idea is that it is a property of empty space itself. According to quantum physics, a perfect vacuum is not truly empty. It is a seething, bubbling sea of virtual particles that constantly pop in and out of existence. This quantum activity could endow every tiny volume of space with a tiny amount of energy, a cosmological constant that creates a repulsive force. As the universe expands and creates more space, more of this dark energy appears, leading to an ever-increasing push. This means the fate of our entire cosmos is tied to this enigmatic force. If dark energy continues to dominate, the universe will expand forever, growing colder and darker until galaxies are ripped apart, and the fabric of spacetime itself is stretched into a vast, silent, and empty void. But if this energy evolves or changes over time, the outcome could be radically different, perhaps ending in a dramatic collapse or a catastrophic rip. Understanding dark energy is not just about mapping the far future. It forces us to confront a deep and troubling conflict between our two most powerful theories of physics. The predicted energy of the quantum vacuum from quantum mechanics is astronomically larger than the tiny value we observe for dark energy. This is perhaps the worst prediction in the history of science, off by a factor of 1 followed by 120 zeros. This enormous discrepancy tells us that something is fundamentally wrong or missing from our understanding. We are being urged to look deeper, to question the very nature of nothingness. What we call empty space may not be empty at all, but a dynamic medium with a rich and hidden structure, a quantum foam bubbling beneath the smooth surface of reality. Even the seemingly smooth stage of spacetime reveals a hidden chaos at its core. Zoom in far enough past atoms, past subatomic particles, and the very fabric of reality may dissolve into a seething, turbulent froth. This is the seventh clue, known as quantum foam, a concept born from the strange marriage of quantum mechanics and gravity. At the unimaginably small Planck scale, a distance so tiny it is a decimal point followed by 34 zeros and then a 1, the calm, continuous fabric described by Einstein is theorized to break down completely. Here, energy fluctuations are so violent that virtual particles blink into and out of existence, creating a chaotic foam where the concepts of here and there, now and then, lose all meaning. For a fleeting instant, a tiny wormhole might form and vanish, or a minuscule region of space might boil with unimaginable energy. This is not empty space. It is a dynamic, effervescent medium, the quantum foam. This idea forces us to question if spacetime is truly smooth and continuous, or if it is ultimately pixelated, woven from tiny, indivisible loops as proposed by theories like loop quantum gravity. While we cannot yet peer directly at this scale, we see its potential fingerprints everywhere. The Hawking radiation that slowly evaporates black holes is a direct result of these quantum fluctuations at the event horizon. The mysterious vacuum energy we call dark energy might be the faint, large-scale echo of this microscopic turmoil. This frothy foundation could be the key to finally uniting Einstein's theory of gravity with the quantum world, creating a single theory of quantum gravity. It suggests that the universe at its heart is not analog but digital, built from the tiniest possible grains of spacetime. And if the fabric of reality is woven from discrete threads, could those threads be pulled apart and reconnected to form tunnels through the cosmos? These theoretical tunnels are not just science fiction, They are mathematically valid features of the cosmic landscape. Wormholes, or Einstein-Rosen bridges, are genuine solutions to Einstein's equations of general relativity. They emerge as shortcuts through the folded fabric of spacetime, potentially connecting two distant points or even two different moments in time. Picture the universe not as a flat sheet, but as a complex, multi-dimensional sculpture. A wormhole would be like a tightly rolled tube connecting the underside of one fold to the top of another, a secret passageway bypassing the long road across the surface. For such a tunnel to be stable and traversable, however, it would require a form of exotic matter with negative energy density. This bizarre substance would have a repulsive gravitational effect, acting like a force field to prop the throat of the wormhole open against its natural tendency to collapse instantly into a black hole. While we have never observed this exotic matter, quantum field theory allows for the possibility of negative energy under specific conditions, offering a tiny glimmer of hope that such structures could exist. The implications are staggering. A stable wormhole would not just allow for near-instantaneous travel across the galaxy, it could also become a time machine. If one end of the tunnel were accelerated to a significant fraction of the speed of light and then brought back, time dilation would cause that end to be younger than the stationary end. Stepping through could mean arriving in a different era. This immediately raises profound paradoxes, like the famous grandfather paradox, where a time traveler could prevent their own existence. The laws of physics seem to abhor such inconsistencies, leading many physicists to propose cosmic censorship conjectures that may prevent wormholes from ever being used in this way. Their potential existence forces us to confront the deepest questions about causality and the fundamental topology of the universe. Could the cosmos be woven together with an invisible network of these bridges? If so, the connectivity of spacetime is far richer and more mysterious than we ever dreamed, suggesting that separations of billions of light years might be an illusion. This incredible idea pushes us toward an even more radical concept, that our entire three-dimensional universe might itself be a projection from a two-dimensional surface, a cosmic hologram. This leads us to a concept so radical it questions the very nature of dimensions. The holographic principle suggests that our experience of a three-dimensional universe might be a magnificent illusion. All the information needed to describe everything within a volume of space, every star, every planet, every one of us, could be perfectly encoded on its two-dimensional boundary. Think of it like the security hologram on your credit card. The flat, shiny surface contains all the data necessary to project a convincing three-dimensional image. In the same way, the universe might be a cosmic projection. This incredible idea emerged from studying the thermodynamics of black holes. When matter falls into a black hole, it seems to vanish, but its information is not lost. Instead, it becomes encoded on the event horizon, the black hole's two-dimensional surface. This suggests that the reality we perceive within the volume is a translation of information stored on the surface. Theories like the AD-SCFT correspondence in string theory provide a mathematical foundation for this. They demonstrate a perfect duality, showing how a theory of gravity operating in a volume of space can be completely equivalent to a quantum field theory operating on its lower dimensional boundary. This means that gravity, and by extension the very fabric of spacetime, might not be fundamental forces. They could be emergent properties, side effects of a deeper, information-based reality playing out on a distant, two-dimensional screen. If this is true, then our entire universe, with its vast galaxies and swirling nebulae, is a hologram. The solidity of the world around you, the feeling of space between objects, it would all be a dense and complex computation. This principle forces us to reconsider what is real. It tells us that information is the most fundamental currency of the cosmos, and that space-time is its magnificent projection. To understand how information shapes reality, we must now confront the universe's tendency toward disorder, a force known as entropy. Even the ultimate cosmic voids are not free from the universal law of disorder. A black hole, the simplest object in the universe defined only by its mass, spin, and charge, appears to be a perfect trap of nothingness. Yet it hides a secret, a deep connection to the quantum world through a property called entropy. Entropy is a measure of chaos, of the number of ways a system's microscopic parts can be rearranged without changing its overall appearance. A tidy room has low entropy, a messy room has high entropy. Stephen Hawking made the stunning discovery that a black hole's entropy is directly proportional to the surface area of its event horizon. The larger the black hole, the more entropy it contains. This was a profound revelation because in physics, entropy is fundamentally linked to information. A system with high entropy contains a vast number of hidden microscopic states. So if a black hole has entropy, it must be storing information about all the things that ever fell into it. Every star, every planet, every atom carries information, and the black hole must somehow preserve it. Hawking then unveiled his next bombshell, that black holes are not eternal. Due to those quantum fluctuations at the edge of the event horizon, they slowly leak radiation and lose mass, eventually evaporating completely over trillions of years. But this created a nightmarish puzzle, the information paradox. If the black hole vanishes, what happens to all that information it was supposedly storing? Quantum mechanics states that information can never be truly destroyed. It can only be scrambled or rearranged. Hawking's original calculations suggested the radiation was random and thermal, containing no information about what fell in. This would mean the information was erased from the universe forever, a direct violation of a core law of physics. For decades, this paradox pitted the two pillars of modern physics, general relativity and quantum mechanics, against each other. How could both be true if they gave contradictory answers about the fate of information? The resolution to this crisis may be the key to unlocking quantum gravity. Modern theories now suggest the information is not lost. It could be encoded on the event horizon itself, imprinted there in unimaginably complex ways, and then slowly radiated back out into the universe in a scrambled holographic form. Other radical ideas propose that the event horizon is not a calm boundary but a searing firewall of energy, or that the black hole's interior is not empty but a giant, tangled ball of strings, a fuzzball. The incredible takeaway is that nothing is ever truly lost in our universe. Information, the most fundamental building block of reality, is permanent. It may be transformed, hidden, or incredibly difficult to read, but it persists. This deep link between space-time and information tells us that the cosmos might fundamentally be a processor of data, and gravity is its language. To trace this data stream back to its origin, we must listen for the oldest signal in the universe, the faint afterglow of creation itself. This faint, cold glow is the oldest light in the universe, a fossilized echo of creation itself. The cosmic microwave background radiation is the 11th profound clue woven into space-time, a snapshot of the infant cosmos when it was just 380,000 years old. At that moment, the universe had cooled enough for atoms to form, allowing light to travel freely for the first time. That first flash of light has been stretching and cooling for over 13 billion years, and it now permeates all of space as a nearly uniform microwave signal. But nearly uniform is not perfect. When we map this radiation with exquisite precision using satellites like Planck, we find it is not a smooth sheet. It is a tapestry of tiny temperature variations, anisotropies, where some patches are ever so slightly warmer or colder than others. These minute fluctuations are the seeds of all cosmic structure. They are the gravitational fingerprints of regions that were slightly denser than others. Over billions of years, gravity amplified these tiny imperfections, pulling matter together to form the very first galaxies, stars, and eventually everything we see today. The specific pattern of these hot and cold spots is a treasure trove of information. It tells us the universe is geometrically flat. It confirms the exact amounts of dark matter and dark energy, and it precisely dates the cosmos at 13.8 billion years old. Most remarkably, these patterns may also contain the faint imprint of primordial gravitational waves. These would be ripples in spacetime generated by the universe's most violent birth pang, a period of hyper-accelerated expansion called inflation. This theory suggests that quantum fluctuations, tiny jitters from the subatomic world, were stretched to cosmic proportions during inflation, becoming the very seeds for galaxies. The cosmic microwave background is our most direct window back to the beginning. It connects the vast cosmic structures we see today to the quantum nature of reality at the smallest scales. By reading this ancient light, we are deciphering the initial conditions of spacetime itself, understanding how the smooth, hot soup of the Big Bang evolved into the complex, structured universe we inhabit. If these anisotropies are the blueprint, then perhaps the universe was built with more dimensions than we can possibly perceive. Our universe might be a shadow of something much larger, playing out in dimensions we cannot see. The idea that spacetime has more than the 4 dimensions we experience, 3 of space and 1 of time, is not science fiction. It is a serious proposal from advanced physics, a potential solution to the deepest mysteries of the cosmos. String theory, for example, requires 10 or even 26 dimensions for its mathematical equations to work consistently. Where are these extra dimensions? The theory suggests they are curled up or compactified into an unimaginably tiny size, far smaller than an atom. Imagine a garden hose. From a distance, it looks like a simple one-dimensional line. But if you could shrink yourself to the size of an ant and crawl on its surface, you would discover it has a second dimension, a circular direction that loops around its circumference. Our universe could be like that. Every single point in our familiar 4-dimensional spacetime might hide a tiny 6-dimensional shape, a Calabi-Yau manifold folded in upon itself. This is not just a mathematical curiosity. These hidden dimensions could explain one of the most perplexing questions in physics: why gravity is so astonishingly weak compared to the other fundamental forces. A small magnet can lift a paperclip, overcoming the gravitational pull of the entire Earth. Why is gravity so feeble? One compelling idea is that gravity is not weaker, it is just spread out. While the electromagnetic force is confined to our 4-dimensional realm, gravity might be the only force that can leak into or propagate through these extra dimensions. Its strength would be diluted, making it seem weak from our limited perspective. We might even be living on a 4-dimensional membrane or brain, floating within a higher dimensional space, with other brains hosting entirely separate universes just millimeters away in a dimension we cannot access. Scientists are actively hunting for evidence. The Large Hadron Collider smashes particles together at incredible speeds, searching for telltale signs like missing energy, which could indicate that gravity or gravitons are escaping into other dimensions. Other experiments look for anomalies in how gravity behaves at microscopic distances, where the influence of these curled-up dimensions might become detectable. If proven, this would be a revolution on par with Copernicus showing we are not the center of the solar system. It would mean our entire reality is a slice, a mere fraction of a far grander, multidimensional cosmos. This hidden architecture suggests that the vacuum of space is not a simple emptiness, but a seething, multidimensional quantum foam. The vacuum of space is not a still and silent void. It is a vibrant, dynamic sea of potential, a quantum stage where particles constantly flicker in and out of existence. These are vacuum fluctuations, the 13th profound clue hidden within spacetime. According to quantum mechanics, empty space is not empty at all. At the tiniest scales, pairs of virtual particles and their antiparticles spontaneously form, borrowing energy from the universe for an immeasurably brief moment before they collide and annihilate, returning the energy and vanishing. This is not a theoretical fantasy. We have direct experimental proof in a remarkable phenomenon called the Casimir effect. If you take two perfectly smooth, uncharged metal plates and place them incredibly close together in a vacuum, they will experience a faint but measurable force pulling them together. Why, in the vast space outside the plates, any wavelength of virtual particles can appear, but in the narrow gap between them, only certain wavelengths can fit. This creates a pressure difference, with more virtual particle activity pushing on the plates from the outside than from the inside. The plates are quite literally pushed together by the restless energy of nothingness itself. This confirms that spacetime has an inherent energy and structure, even in its lowest possible energy state. This quantum activity is not just a microscopic curiosity. It influences the behavior of all particles and may even hold the key to the universe's accelerating expansion. The vacuum energy from these endless fluctuations is a prime candidate for the mysterious dark energy that is pushing the cosmos apart. This means the fate of the entire universe could be dictated by the faint, seething hum of empty space. Every cubic centimeter of the vacuum around you is teeming with this transient energy, a reminder that nothingness is full of potential, and that existence itself may have emerged from this restless quantum foam. To understand the ultimate limits of this fabric, we must now confront the points where its rules break down completely, the terrifying and enigmatic singularities. At the very heart of a black hole, and at the very beginning of the universe, our understanding of reality shatters. These are singularities, points where the density of matter and the curvature of spacetime are predicted to become infinite. According to the equations of general relativity, gravity wins its ultimate victory here, crushing all matter into an infinitely small point of zero volume. But in physics, infinity is not an answer, it is a sign that our theory has reached its breaking point. A singularity is a place where the known laws of physics simply cease to apply, where the concepts of space and time lose all meaning. It is the ultimate edge of our map, a blank spot labeled "Here be dragons." Yet these cosmic boundaries are not dead ends. They are profound clues screaming that we need a deeper theory, one that can blend gravity with the quantum world. Some approaches, like loop quantum gravity, suggest that singularities are an illusion. They propose that at the center of a black hole, or at the moment of the Big Bang, quantum effects take over, creating a repulsive force so powerful that it prevents the infinite collapse. Instead of a singularity, the Big Bang might have been a big bounce, a moment of immense rebound from a previous universe that had contracted. This idea elegantly avoids the need for a true beginning, suggesting our cosmos is just one cycle in an eternal sequence. The quest to understand singularities is the quest to understand the origin of spacetime itself. It forces us to ask what happened before the Big Bang and what truly lies at the center of a black hole. These are not just abstract questions, they are the keys to a theory of everything. If we can gracefully describe these cosmic boundaries, we will have finally unified the largest and smallest scales of existence. This journey into the extreme forces us to confront the nature of time itself and why it seems to flow in only one direction throughout the universe. The laws of physics do not seem to care which way time flows. A video of two planets orbiting a star looks just as natural when played in reverse. A recording of two particles colliding and bouncing apart makes perfect sense whether you watch it forward or backward. Yet we all experience time moving in one direction only, an inexorable march from the past into the future. This is the arrow of time, the 15th profound clue written into the fabric of spacetime. The universe has a clear preference for this direction, and that preference is deeply tied to a concept we call entropy, the measure of disorder. The cosmos is on a one-way journey from a state of low entropy, of high order, toward a state of maximum entropy, of ultimate chaos. This all started with the Big Bang, which was a moment of incredibly low entropy, an extraordinarily ordered and unlikely state. That initial condition set the cosmic clock ticking. As the universe expands and matter spreads out, entropy increases, creating the forward flow of time we all experience. This is why we remember the past but not the future, why an egg can scramble but never unscramble itself. The arrow of time is not a fundamental law written on a stone tablet. It is an emergent property, a story that unfolds because of the specific initial conditions of our universe. Near a black hole, this concept is twisted to its extreme. For an observer falling toward the event horizon, time would appear to slow to a crawl relative to the outside universe. From their perspective, they cross the threshold in a finite time, while from our perspective, they are frozen there forever, their image slowly red shifting into oblivion. This reveals that the arrow of time is not absolute. It is a local experience shaped and warped by the gravity wells and contours of spacetime. The expansion of the universe itself may be the ultimate engine driving the increase in entropy, creating more room for disorder to grow and ensuring time's arrow continues to fly forward. This clue forces us to confront a humbling truth. Our perception of time, of cause and effect, of memory and anticipation, is not a universal constant. It is a direct consequence of the universe's structure and its journey from a highly ordered beginning toward an uncertain future. We are not just observers of time, we are participants in its grand, irreversible narrative. Even light itself must pay a toll to escape a powerful gravitational field. This is the phenomenon of gravitational redshift, a subtle but crucial clue that spacetime curvature alters the very essence of light. As a photon struggles to climb out of a deep gravity well, like that around a neutron star or a black hole, it loses energy. Since a photon's energy is directly tied to its color, this loss causes its wavelength to stretch, shifting it toward the red end of the electromagnetic spectrum. The photon does not slow down. Light always travels at the same speed, but it becomes redder and dimmer, its energy sapped by the immense gravitational pull. This effect was first confirmed in a brilliant laboratory experiment here on Earth. Physicists Robert Pound and Glenn Ribka fired gamma rays down a tower at Harvard University. They measured a tiny but precise redshift in the light that had traveled downward, fighting Earth's gravity, compared to the light that traveled upward. This was a direct, earthly validation of Einstein's prediction. In the cosmos, this redshift becomes a powerful diagnostic tool. When we observe the light from a white dwarf star, we can measure its gravitational redshift. The amount of reddening directly tells us the star's mass, allowing us to weigh these incredibly dense stellar embers from across the galaxy. This is how we confirm that some neutron stars pack more than the mass of our Sun into an object just a few miles across. The light we receive from them is profoundly redshifted, carrying the unmistakable signature of an unimaginable gravitational grip. This clue reveals that gravity does not just bend the path of light through lensing, it also stamps its fingerprint directly onto the light's energy. By reading this signature, we can measure gravitational fields we cannot see, mapping the distribution of mass throughout the universe. It is a direct testament to the fact that gravity and light are inextricably linked through the warping of spacetime. And if a massive object can stretch the light escaping from it, what happens when that object begins to spin, dragging the very fabric of reality around with it? A spinning planet does more than just move through space. It actively pulls the fabric of spacetime along with it. This phenomenon is known as frame dragging, and it is the 17th clue woven into the cosmic tapestry. Massive rotating objects, from our own Earth to the most violent black holes, do not simply sit within the static grid of spacetime. Their spin creates a vortex, a subtle whirlpool in the fabric of reality that drags the very framework of space and time around with them. It is as if the universe itself is a vast, viscous fluid, and a spinning sphere creates a current that pulls everything nearby into its rotation. This effect, also called the lens-Thirring effect, was predicted by Einstein's equations but was so minuscule that it seemed nearly impossible to measure. That changed with the Gravity Probe B mission, a technological marvel of precision. The satellite carried incredibly sensitive gyroscopes, their spinning rotors polished to near atomic perfection. As it orbited our rotating planet, the delicate orientation of these gyroscopes was ever so slightly altered by the invisible current of frame dragging. The shift was tiny, equivalent to watching a gyroscope on Earth drift just 1 degree every 100,000 years, but it was there. This confirmed that even our gentle, spinning Earth leaves its mark on spacetime. Now amplify this effect to a cosmic scale. Around a rapidly spinning black hole, frame dragging becomes a dominant and terrifying force. It creates a region outside the event horizon called the Ergosphere, where spacetime itself is whipped into a furious vortex. Nothing here can stand still. The dragging is so powerful that any object is forced to move in the direction of the spin. But this maelstrom also presents a bizarre opportunity. In a theoretical process known as the Penrose process, an object could enter the ergosphere and split in two. One piece could be flung into the black hole with negative energy, while the other is catapulted out with more energy than it entered with. This is how energy could be extracted directly from the rotation of a black hole, a process that might power the incredible jets of superheated matter seen in quasars, the most luminous objects in the universe. Frame dragging reveals that rotation is not an isolated property. It is a fundamental interaction that imprints itself on the geometry of the cosmos, influencing the orbits of planets, the behavior of stars, and the evolution of entire galaxies. It shows us that spacetime is not a passive stage but a dynamic participant, twisted and shaped by the spin of everything within it. This subtle twisting of the cosmic fabric hints at even stranger topological defects that might be hidden within it, theoretical flaws in spacetime itself known as cosmic strings. These hypothetical flaws in spacetime are not made of any ordinary material. Cosmic strings are thought to be incredibly thin, perhaps no wider than a proton, but stretching across the entire observable universe. Their density is unimaginable. A single inch of such a string could weigh as much as a mountain range. They are not cosmic yarn, but more like cracks that formed in the fabric of reality as the universe cooled and underwent dramatic phase transitions in its earliest moments. Just as water freezing into ice can create cracks and fissures, the rapid cooling of the fundamental forces may have left behind these one-dimensional topological defects, permanent wrinkles frozen into the very geometry of spacetime. If they exist, their gravitational influence would be profound. a cosmic string drifting through space would not pull objects toward it with a standard gravitational field. Instead, its immense mass would slice through spacetime, creating a unique kind of lens. Light from a distant galaxy passing on either side of the string would be bent, potentially creating a perfect double image of the same object, a telltale signature astronomers are actively searching for. These cosmic scars might also vibrate and oscillate, sending out powerful ripples in space-time, gravitational waves that could be detected by observatories like LIGO. Finding even a single cosmic string would be a direct window into the highest energy physics, a relic from a time when all the forces of nature were unified into one. It would provide stunning evidence for theories that go far beyond the standard model, revealing the specific symmetry-breaking patterns that shaped the infant cosmos. Their potential existence is a powerful reminder that the universe's history is not just written in the stars, but is literally carved into the geometry of space-time itself. The largest structures we see today, vast filaments of galaxies stretching across the void, might even trace their origins back to the gravitational seeds planted by these ancient strings. This idea pushes us to a truly radical frontier, the possibility that spacetime is not a fundamental stage, but something that emerges from a deeper, more fundamental layer of reality, a reality built from the connections between particles. The very geometry of space and time may be a direct consequence of a deeper quantum connection. This 19th clue proposes that spacetime itself emerges from quantum entanglement, that spooky action at a distance that so troubled Einstein. Entanglement is the strange phenomenon where two particles become linked, their fates intertwined no matter how far apart they are separated in the universe. A measurement performed on one instantly influences the state of the other, a connection that seems to defy the speed of light. But what if this bizarre quantum link is not just happening within spacetime, but is actually responsible for creating spacetime? This radical idea suggests that the distance between 2 points, the smooth fabric we move through, is woven from the sheer number of entangled connections between the underlying quantum bits. The more entangled two regions are, the closer they are in spacetime. Areas and volumes in space may be directly proportional to something called entanglement entropy, a measure of the quantum information shared between them. We see strong hints of this in black hole physics, where the information content of a black hole is proportional to the area of its event horizon, not its volume. This points to a holographic universe where the three-dimensional world is a projection from a two-dimensional surface, and that projection is built entirely from entangled quantum data. Scientists are now trying to test this in laboratories using sophisticated setups with ultra-cold atoms or other quantum systems. By precisely controlling and measuring the entanglement between particles, they hope to see if geometric properties like distance and curvature actually emerge from these quantum connections. If this is true, it means that the stage upon which the universe plays out is not fundamental. Spacetime is not the starting point of reality. It is a secondary effect, a collective illusion that arises from a vast, invisible network of quantum information. The solid ground beneath your feet, the vast emptiness between stars, all of it would be the result of an unimaginably complex web of quantum links. This is perhaps the most profound bridge yet between the quantum world and gravity, suggesting that the universe is not made of stuff, but of relationships. It forces us to ask why this particular network of information produced a universe with exactly the right properties for us to exist within it. The precise values of nature's constants seem almost too perfect to be an accident. The strength of gravity, the mass of an electron, the exact speed of light, if any of these were altered by even a minuscule fraction, the universe as we know it would cease to exist. Stars would not form, complex atoms would be impossible, and life could never arise. This extraordinary fine-tuning is the 20th profound clue, and it forces a deeply philosophical question. Why does the fabric of spacetime have exactly the right properties to allow for us? One compelling answer is the Anthropic Principle, which simply states that we observe a universe compatible with observers because we are here to observe it. This suggests a staggering possibility that our cosmos might be just one bubble in a vast multiverse. In this infinite ensemble, every possible set of physical laws and constants is realized in some universe. Most of those universes would be stillborn or barren, but in a rare few like our own, the conditions are just right for galaxies, planets, and life to emerge. This idea finds a home in theories like string theory's landscape, which predicts a colossal number of possible vacuum states, each with different physical properties. Spacetime's specific curvature, its rate of expansion, even the number of dimensions we experience, might not be fundamental truths, but simply the local bylaws of our cosmic neighborhood. This shifts the question from why our universe is fine-tuned to why we find ourselves in this particular tuned universe. It is a clue that challenges the boundary between physics and philosophy, pushing us to ask if the laws of nature are inevitable or a spectacularly lucky roll of the dice. The architecture of reality itself may be contingent, a random selection from an infinite menu of possibilities. But if our universe is one possibility, could there be others that are its perfect opposite, where time itself flows backward? If a black hole is a cosmic drain from which nothing returns, a white hole would be its impossible opposite. These theoretical objects are regions of spacetime where matter and energy can only pour outward, forever refusing any entry. They are not just cosmic fountains, they are one-way exits written directly into the geometry of the universe. White holes emerge as perfect mathematical solutions to Einstein's equations of general relativity, the time-reversed twins of their black hole siblings. While no white hole has ever been observed, and many physicists doubt they could form in our universe, their possibility forces us to confront the deep symmetries of physical law. The equations governing reality do not inherently prefer one direction of time over the other. They work just as well if time were to run backward. A white hole would be the ultimate expression of that symmetry, a place where the universe's relentless march toward higher entropy is seemingly reversed. Some speculative theories propose that a black hole singularity, when treated with the laws of quantum gravity, might not be a final end point. Instead, it could transform, funneling all the matter it ever consumed into a new region of spacetime as a white hole, a big bang for a tiny baby universe. This would mean every black hole in our cosmos could be the birthplace of an entirely new reality, with its own spacetime and physical laws. Others suggest that the two ends of an Einstein-Rosen bridge wormhole could be a black hole for entry and a white hole for exit, though keeping such a tunnel stable remains a monumental challenge. Contemplating white holes stretches our imagination to its breaking point. It asks us to envision a universe where cause and effect are inverted, where shattered cups reassemble on the floor and leap back onto tables. While they may never be more than a mathematical curiosity, white holes serve a vital purpose. They are a thought experiment that challenges our most basic assumptions about causality, the arrow of time, and the very nature of singularities. They remind us that the fabric of reality might be woven with stranger threads than we can possibly see, and that our understanding of the cosmos is still in its infancy. This journey into the extreme edges of theory prepares us for a clue that operates at the very smallest scales, where the quantum world and the vast cosmos meet in a surprising way. A single electron can be in two places at once, a ghostly superposition that defies common sense. This is the bizarre reality of the quantum world. But look at the world around you. Chairs and tables exist in definite positions. They do not blur into multiple locations. The process that bridges these two realities is called quantum decoherence, and it is the 22nd clue woven into the fabric of spacetime. A quantum system left perfectly isolated will happily maintain its superposition, but the moment it interacts with its environment, whether through a stray photon or a passing atom, that fragile quantum state collapses. Information about the superposition leaks out, and the system is forced to choose a single, classical state. It is the difference between a perfectly still pond and one rippling with disturbances. The still pond can clearly reflect many possibilities, but the disturbed one shows only a single, jumbled image. For decades, this was seen as a process that just happens within spacetime. But a radical new idea suggests spacetime is not a passive container. It might be the very cause. Could gravity itself, the curvature of spacetime, be the ultimate source of decoherence? Some theories propose that the gravitational field of a massive object, or even the expansion of the universe, continuously measures quantum systems, forcing them to collapse into a single reality. Scientists are testing this at the very edge of what is possible. They are firing large, complex molecules through interferometers, watching to see at what size and mass these quantum superpositions simply vanish, succumbing to decoherence. Future experiments aim to place tiny crystals into superposition, creating a situation where the crystal's own gravity might cause its quantum state to collapse. If gravity is indeed responsible for decoherence, it would be the missing link between the quantum world and the cosmic scale. It would mean that spacetime is not just the stage for the quantum drama, it is a lead actor, actively participating in the creation of the definite world we perceive. This process may be the reason the universe appears solid and classical to us, emerging from a fuzzy quantum foundation. But if our universe is just one possible outcome, what about all the others that could have been? This leads to a staggering idea that our entire cosmos might be just one bubble in an infinite, ever-growing froth of universes, a concept known as eternal inflation. The expansion that birthed our universe might be a process without end. The theory of inflation describes a period of hyper-accelerated expansion in the first fraction of a second after the Big Bang. This event smoothed our universe and planted the seeds for galaxies. But what if this inflationary process is not a one-time event? What if it is eternal? In this model, the quantum foam of spacetime is like a pot of water that is forever boiling. Most regions eventually cool and settle into stable universes like our own, but the inflationary process itself never stops. New bubbles of spacetime are continuously nucleating, each one a separate universe with its own unique properties. In this infinite multiverse, the fundamental constants of nature, the strength of forces, and even the number of spatial dimensions could be different in every single bubble. Some universes might have gravity so strong they collapse instantly. Others might have no atoms and be utterly dark and barren. Our universe, with its specific, life-permitting constants, would be just one rare possibility in an unimaginably vast cosmic landscape. The patterns we see in the cosmic microwave background, the specific distribution of those hot and cold spots, provide tantalizing hints that this eternal inflation might be real. This idea is both exhilarating and humbling. It means our entire observable cosmos, with its hundreds of billions of galaxies, is just a single bubble in a meta-universe that has no end. Spacetime itself is not a static stage, but a dynamic, generative engine, endlessly giving birth to new realities. This pushes the very boundaries of science, challenging us to find ways to test the untestable and to ask if our universe is truly unique or simply one possibility in an infinite ensemble. If reality is this vast, then information itself must have a fundamental limit, a maximum amount that any region of space can possibly contain. The total amount of information any volume of space can hold is not limitless. This is the holographic entropy bound, a profound principle that tells us the maximum entropy, or chaos, a region can contain is not determined by how big it is on the inside, but by how big it is on the outside. The information capacity is set by the surface area of its boundary. We first saw this with black holes, where all the information about what fell in is somehow encoded on the two-dimensional surface of the event horizon. The mind-bending implication is that this rule might apply everywhere: a sealed room, a planet, even an entire galaxy. The total amount of information it can possibly contain, every atom, every photon, every thought, is limited by the area of its walls. You could not possibly pack more data into a 1-meter cube than you could write on its 6 outer surfaces. This suggests that the three-dimensional world we experience, with its rich depth and volume, might be a magnificent projection from a vast, complex, two-dimensional surface at its boundary. The universe is not a boundless hard drive. It has a finite data limit, and that limit is set by its skin. This discovery forces us to confront a startling possibility, that space-time itself might not be smooth and continuous, but might instead be woven from tiny, indivisible pieces, the fundamental atoms of reality. The smooth geometry of Einstein's universe may be a beautiful approximation, a grand illusion masking reality's true pixelated nature. At the very smallest scales, far beyond our ability to see, space-time itself could be woven from fundamental, indivisible units. These are the atoms of space-time, the 25th profound clue. In theories like loop quantum gravity, the fabric of reality is not continuous and infinitely divisible. It is composed of tiny, one-dimensional loops, vibrating and connecting to form a dynamic network. This granular structure would mean there is a smallest possible unit of space, a volume so tiny it is a trillion times smaller than an atom. There is also a smallest possible unit of time, a single tick of the cosmic clock at the Planck scale. This solves the problem of singularities, those points of infinite density at the center of black holes. In this view, matter cannot be crushed to an infinitely small point. Instead, the repulsive force generated by these space-time atoms prevents total collapse, replacing the terrifying singularity with a dense but finite core. This granularity suggests the universe is not analog but digital, a vast computation where geometry emerges from the relationships between these fundamental quanta. We see hints of this in the black hole information paradox, where entropy is tied to surface area, not volume, pointing toward a reality built from a network of information. If this is true, then motion itself might not be perfectly smooth, but a series of tiny, discrete steps like the frames of a film. While we cannot yet probe these scales directly, the mathematics points toward a universe where the smooth stage of relativity gives way to a buzzing, vibrating network at the foundation of everything. This idea brings us to the final frontier, the ultimate observer in this cosmic drama. If reality is a computation, a network of information, who or what is processing the data? Our own minds might be the most complex space-time detectors in the known universe. The final clue brings us inward, to the very consciousness that observes this cosmic tapestry. We experience a smooth, continuous flow of time and a vast, three-dimensional space, but this is a construction, a brilliant simulation running inside our skulls. Our brains are not passive cameras recording reality. They are active editors, stitching together a coherent narrative from a chaotic flood of sensory data. Neurological studies show there is a slight delay between an event occurring and our conscious awareness of it. Our mind constantly predicts the immediate future, creating the illusion of a seamless present. This means the flow of time we feel so deeply is in part a neurological artifact. This internal experience intersects with a profound question from quantum physics, the observer effect. In the famous double-slit experiment, the behavior of a particle changes when it is being observed. Does the conscious act of measurement itself force a fuzzy quantum possibility to snap into a definite reality? This has sparked intense debate about the role of the mind in shaping the cosmos. Is spacetime a fundamental stage that exists independently of us, or could it be that our perception is somehow necessary to bring it into focus? These are not questions with easy answers, and they venture far from established science into the realms of philosophy and metaphysics, but they serve as a powerful reminder. Every clue we have explored, from gravitational waves to dark energy, is ultimately filtered through human perception and interpreted by human consciousness. We are not separate from the spacetime we study. We are a product of it, and in a way we do not yet understand, we may also be participants in its ongoing creation. This final mystery invites us to ponder the deepest connection of all, the bond between the observer and the observed, between the mind and the cosmos. Our journey through these 26 clues reveals a cosmos far stranger and more wonderful than we ever imagined. We have felt the ripples from colliding black holes, peered into the abyss of singularities, and traced the ghostly influence of dark matter. We have watched time itself stretch and warp, and questioned if our reality is a holographic projection from a distant, two-dimensional surface. Each mystery, from the quantum foam to the multiverse, is a thread in the same magnificent tapestry, a tapestry we call spacetime. These are not just abstract puzzles for physicists, they are fundamental questions about the nature of existence itself. Who are we, and what is this reality we find ourselves in? Every observation, every experiment, and every bold theory brings us one step closer to a deeper truth, to a unified understanding of the cosmos. I would love to know which of these clues resonated most deeply with you. Share your thoughts in the comments below. If you enjoyed this journey to the edge of understanding, please subscribe for more explorations into the great mysteries of space and time. Thank you for joining me on this adventure. Never stop looking up and never stop questioning the nature of reality itself.